December 15, 1944, 5:42 p.m. off the coast of Luzon, Philippine Sea. The sky is low and grey. The sea heaves under a rising wind. On the deck of a United States Navy destroyer, sailors brace themselves as the general alarm screams. Look out, shout bearings. Engines rumble harder. Far out, dark shapes break through the clouds. They are coming fast, too fast. Japanese aircraft dive out of the overcast. Engines howl. Tracer fire reaches up, red and white lines tearing the air. The ship rolls. Salt spray hits the gun shields. A 5-inch gun swings, not by human hands alone, but by a system of wires, gears, and spinning cams hidden deep inside the ship. A bell rings. The director locks on. The guns elevate. The barrels stop shaking. Fire. Shells burst ahead of the diving planes. Not behind, not guessing, ahead, the explosions form a wall of steel and flame. One aircraft flies straight into it and disappears. Another shears a wing and spirals into the sea. Japanese pilots had faced anti-aircraft fire before. They expected wild barrages, guesswork, human delay. This is different. The guns seem to know where they are going. In that moment, above the rolling sea and burning wreckage, a new kind of warfare reveals itself. And this moment is only the beginning of a much larger story. If you want more stories like this, make sure to subscribe, like, and share. The origins of this system stretch back years before the Pacific War exploded. During the interwar period, naval planners faced a growing threat. Aircraft were becoming faster, higher flying, and deadlier. A single bomb could cripple a battleship. Manual aiming and simple optical sights were no longer enough. The United States Navy began searching for a solution. Not a bigger gun, but a smarter one. Engineers at the Ford Instrument Company and Bell Telephone Laboratories worked with the Navy Bureau of Ordnance to solve a hard problem. How do you hit a fast-moving aircraft from a moving ship, with both target and platform in motion, while accounting for wind, range, speed, and gravity? The answer was a mechanical analog computer. By the late 1930s, this effort produced the Mark 37 gunfire control system, paired with the Mark 1 fire control computer. The system used optical rangefinders, later radar, to track a target. The computer processed target speed, bearing, altitude, and course. It calculated where the aircraft would be when the shell arrived. Then it aimed the guns automatically. The main weapons were dual-purpose 5-inch 38 caliber guns. Each shell weighed about 55 pounds. The guns could fire up to 15 rounds per minute. They reached altitudes over 37,000 feet. On their own, they were powerful. Guided by the computer, they became precise. Early radar sets, like the Mark IV and later the Mark XII, allowed tracking through clouds and darkness. For the first time, a ship could fight aircraft it could barely see. This system was designed for fleet defense. Carrier task forces depended on it. Without it, aircraft carriers were vulnerable. With it, they had a fighting chance. When war came to the Pacific, the system was ready. But readiness did not mean immediate success. Early in the war, many crews did not trust the new technology. Gunnery officers were trained to rely on their eyes and experience. Some believed machines could not replace judgment. Training was uneven. Crews often had less than 100 hours on the system before deployment. In combat, switches were misused. Inputs were wrong. Range data lagged behind fast targets. During the early battles of 1942, including around Guadalcanal, anti-aircraft fire was often heavy but ineffective. Japanese pilots flew through flak bursts with confidence. After-action reports noted that bursts were consistently behind the target or poorly timed. Radar tracking was new and fragile. Salt spray damaged antennas. Power fluctuations caused dropouts. When radar failed, crews reverted to optics, losing the computer's advantage. There were accidents too. In one training exercise off Hawaii, a destroyer fired too low during a drill and nearly struck another ship. The report blamed improper synchronization between the director and the computer. Japanese pilots mocked American anti-aircraft fire in early encounters. One pilot wrote that U.S. ships threw shells like blind men throwing stones. Another noted that bursts were loud but easy to dodge. Losses reflected the learning curve. In early 1942, Japanese air attacks often pressed home, despite heavy fire. At Coral Sea and Midway, American ships were hit repeatedly. Anti-aircraft kills were claimed, but confirmation was difficult. The system was powerful, but only if crews learned to trust it, maintain it, and use it correctly. That learning came through hard experience. By late 1942 and into 1943, training improved. Gunnery officers learned to let the computer lead the fight. Crews drilled endlessly. Tracking drills, radar calibration. Communication between the director, plotting room, and gun mounts became faster and cleaner. One key realization was centralization. Instead of each gun acting on its own, the entire battery worked as one. The director tracked a single target. The computer solved the problem. All guns fired together. Data showed the difference. Engagements where the system stayed locked produced burst patterns ahead of targets, not chasing them. Pilots flew into flak instead of away from it. Radar proved critical. With radar tracking, the system could maintain a solution even during evasive maneuvers. At ranges beyond visual sight, guns could still fire accurately. The introduction of the proximity fuse in late 1940 changed everything. Instead of detonating by time or impact, the fuse exploded when it sensed metal nearby. A miss of 70 feet could still destroy an aircraft. Combined with the fire control computer, kill rates jumped. Reports showed that with proximity fuses, one aircraft was destroyed for every 300 rounds fired. Earlier, it had taken thousands. Commanders adjusted tactics. Ships formed layered defenses. Destroyers screened carriers. Cruisers provided heavy fire. Battleships added massive volume. By 1944, the system was no longer experimental. It was trusted. Crews spoke of it as another member of the ship. Japanese pilots began to notice. The first legendary test came during the Battle of the Philippine Sea in June 1944. American carrier task forces faced a massive Japanese air attack at stopping the invasion of the Marianas. Over 2 days, more than 400 Japanese aircraft launched. Many pilots were poorly trained, but the threat was real. As waves approached, American radar picked them up at long range. Ships went to general quarters, directors locked on. As the planes closed, the sky filled with controlled bursts. Not random fire, patterns, walls of explosions at set altitudes. A destroyer escort reported engaging a formation of dive bombers at 12,000 feet. The director tracked the leader. The computer adjusted for speed and dive angle. At 8,000 yards, the guns opened fire. 3 planes disintegrated in the first minute. Others broke formation. Some dove too early, some turned away. Carrier pilots watching from below called it a turkey shoot. By the end, Japanese losses were catastrophic. Over 300 aircraft were destroyed. American ships suffered minimal damage. One Japanese survivor later recalled that the shells exploded where we were going, not where we were. Another encounter came off Okinawa in April 1945. This time, the threat was different. Kamikaze attacks. On April 6th, the largest mass kamikaze attack of the war began. Hundreds of aircraft aimed directly at ships. They did not evade. They did not turn away. The fire control system faced its ultimate test. A radar picket destroyer took station north of the fleet. Its job was to warn of incoming attacks. It was also the first target. At 4:30 p.m., radar contacts multiplied. The director tracked the nearest, guns elevated to maximum speed. The computer worked constantly as targets closed fast at low altitude. Explosions tore through the sky just ahead of the attackers. Some planes flew straight into the bursts and vanished. Others were shredded, but kept coming. A kamikaze broke through and struck the ship near the bridge. Fire erupted, the ship slowed, but the guns kept firing. Despite damage, the fire control system continued to operate. Power was rerouted. One director was lost, but another took over. More attackers fell. In that single engagement, the ship's guns were credited with destroying at least 6 aircraft. Nearby ships added dozens more. Not all were stopped. Losses were heavy. But without the system, losses would have been far worse. A third encounter occurred in the night skies, off Leyte Gulf, in October 1944. Japanese aircraft attempted a surprise night attack. Before radar-guided fire control, night attacks were deadly. This time, radar directors tracked targets through darkness and rain. At 10:12 p.m., a cruiser detected contacts at 15,000 yards. The director locked on. The computer adjusted for wind and ship motion. Guns fired blind into the dark. Suddenly, explosions lit the clouds. Wreckage fell burning into the sea. Pilots never saw the ship they attacked. One American sailor said quietly, "It's like we can see them even when we can't." These encounters showed a pattern. When the system worked as designed, it changed the balance of air defense. The strategic impact was enormous. By 1944, most U.S. warships carried the Mark 37 system or similar variants. Over 8,000 5-inch 38 guns were produced during the war. Thousands of fire control computers were built. Training pipelines expanded. Crews spent hundreds of hours drilling. Maintenance crews kept systems calibrated despite heat, vibration, and battle damage. Compared to Japanese ships, the difference was stark. Japanese fire control relied more on optics and less advanced radar. Their proximity fuses lagged behind. Coordination was weaker. American carrier task forces could sustain high sortie rates because ships survived attacks. Fuel, aircraft, and pilots remained in action. Industrial output made replacement possible. Lost directors were replaced. Improved radar sets were installed. Software changes were made in the form of new cams and gears. The system did not win the war alone, but it protected the ships that projected power across the Pacific. Psychologically, the effect on Japanese pilots was severe. Survivors spoke of invisible hands guiding the fire. One diary entry described American flak as alive. Another pilot wrote that the bursts followed us even when we turned. Slang names emerged. Some called it the steel net. Others referred to ships as spitting demons. Kamikaze pilots were briefed to ignore flak and press on. Even so, many flinched when bursts appeared directly ahead. Some lost control in the shockwave. Morale suffered. Pilots knew that skill and bravery were no longer enough. A machine was predicting their future position. American crews felt the opposite. Confidence grew. Gunners trusted the system. Fear remained, but it was tempered by belief in their tools. One sailor said, "If the director has him, he's already dead." As the war progressed, the system evolved. Radar improved. The Mark 12 and Mark 22 radar sets provided better accuracy and resistance to jamming. Fire control computers were refined for faster targets. Low-altitude tracking improved to counter kamikazes. Backup power systems were added. Guns received improved mounts with faster traverse. Ammunition handling became quicker. Proximity fuses were refined for reliability. Doctrines shifted. Ships practiced massed fire against single threats. Radar picket tactics were adjusted to reduce losses. By 1945, the system reached its most mature form. It was not perfect. It could be overwhelmed. It required skilled crews, but it represented the peak of mechanical fire control. When the war ended, its legacy was clear. Thousands of enemy aircraft had been destroyed by guns guided by fire control computers. Countless ships had survived attacks that once would have sunk them. Japanese pilots who survived spoke with respect. One former aviator said, "We fought brave men, but also their machines. The machines were always ready, The fire control system began as an experiment. It faced doubt and failure. In the end, it became a shield that saved fleets. Its legacy is simple and enduring. It marked the moment when prediction and precision changed naval warfare forever.